a homecoming event where we have the honor of hosting one of our most distinguished faculty members in the College of Chemistry, Professor Omar Yaghi. But before I do that, allow me to take a moment to introduce myself. My name is Dean Tost. I am the Gerald E.K. Branch Distinguished Professor of Chemistry at Berkeley and the current chair of the Department of Chemistry here at Cal. I want to extend my heartfelt gratitude to each and every one of you for being here. Your presence is a testament to your ongoing commitment to the education and research here at Cal, and also giving you an opportunity to hear about an exciting venture that's close to all of our hearts, if you'll allow me a few minutes. Our renowned faculty, including Professor Yaghi, continue to bring forth invaluable insights through their research, taking a collective step forward to transformative initiatives that will help our state, our country, and the planet address some of the issues facing humanity today, including human health and climate change. These faculty initiatives have been a beacon of innovation and collaboration. They're the need of a beacon of innovation and collaboration to call a home. And as such, we in the College of Chemistry have embarked on a journey to build a new infrastructure, a new building in the College of Chemistry, which will be called Heathcock Hall. This endeavor is part of a capital campaign, a monumental effort to build the first new building in the College of Chemistry complex in decades. And the resources to need, and will provide the resources needed to foster the groundbreaking research, nurture the budding talent, both in undergraduates and the graduate students that we train in the College of Chemistry, and to propel us into a future of limitless possibilities that have been inspired through much of the research that's gone on here on Cal for generations. The funds raised for Heathcock Hall will play an integral role in turning this vision of providing this type of space for research and teaching into reality, where our faculty and the research can serve as the intellectual nourishment and the catalyst for the progress that we need. And as Professor Yaghi's lecture will undoubtedly show us an example of that today. I'll take a few minutes to try and introduce Professor Yaghi. He is a true luminary in the field of chemistry. He received his PhD from the University of Illinois at Urbana-Champaign, and then was an NSF postdoctoral scholar at Harvard University before starting his independent career. He currently holds the James and Neil G. Tretter Professorship of Chemistry and is a senior faculty member at the Lawrence Berkeley National Laboratory at the same time. His contributions to the world of chemistry have been nothing short and continue to be nothing short of groundbreaking and remarkable. He is widely known for developing an entirely new field of chemistry called reticular chemistry and being the pioneer in remarkable new materials, including metal organic frameworks, covalent organic frameworks, and zeolitic imidazolate frameworks. So these continue to be one of the most heavily researched areas and most impactful areas in chemistry today. Beyond his research, Professor Yaghi is a visionary leader in many other aspects. He is the founding member of the Berkeley Global Science Institute, a venture that's dedicated to building research centers in developing countries such as Vietnam, and providing opportunities for young scholars from those countries to discover and learn chemistry from him and his peers. He also co-directs the Kavli Energy Nanoscience Institutes, which focus on basic science for energy transformations at the molecular level, and is a key figure in the California Research Alliance with BASF, known as CARA, which supports joint academic industrial ventures to take some of the inventions at Berkeley and transform them into practical solutions. Professor Yaghi's distinguished career has earned him recognition on the global scale. Far too many for me to note here. I will say he is an elected member of the National Academy of Sciences, the German National Academy of Sciences as well, and received many awards, including the Wolf Prize in Chemistry in 2018. Today, we are fortunate to have Professor Yagi share his expertise with us in a lecture entitled Molecular Harvesters for Carbon and Water from Air. But before we do that, I would like to, here we go, remind everyone that Berkeley is on Ohlone land, and please take a minute to read this. In the meantime, please join me in welcoming Professor Yagi.
Thank you, Dean, for that generous introduction. And thank you for your leadership and for taking the time from your research and teaching to lead our department. I share the same floor for my research labs with Dean, and I don't think I can ever find somebody more brilliant and, quite honestly, just a great person to have as a neighbor. So it's in our endeavors, as you get older and older, colleagues become much more important than ever before. And I'm very lucky to have met and enjoy the companionship of Dean and his intellectual insights into chemistry. So I want to talk about, the subject of my talk is really about how science can solve societal problems. No matter how hard they are, science can solve them, and in particular, how chemistry is well suited to do just that. And more importantly, how chemistry at Berkeley, being the #1 chemistry department in the world, can actually solve some of our most pressing problems. And you detected from my title that I'm going to be capturing carbon dioxide from air and from flue gas before it reaches the air, as well as trying to solve the water stress problem in the world. Our planet is in trouble, and many of you watch the news, and I don't need to tell you that, but just in case you haven't watched the news, I just want to show a few slides about what I mean. The Great Barrier Reef, indicated here in these dark spots, half of it is already dead. Actually, it's already bleached because the algae no longer likes it to live there, and therefore it's bleached because of the warm waters. And the darker the color you see here, the more likely that those corals will die. And in fact, this is, you can see here a healthy coral with beautiful, brilliant colors, and a bleached one. And I learned recently that the World Heritage Site list might add this into the endangered list. I don't know if they've done that, but there's definitely debating on whether the Great Barrier Reef is going to be listed as an endangered place. So that's too bad. That's one of the most beautiful things on our planet. And if you watch the news, you know that climate change is no longer a distant thing. It's really impacting lives and livelihoods in most part of the world. And this plot here, you see the weather events. The larger the red is, the more severe that weather event is. On average, in recent years, land heat waves, ocean heat waves, wildfires, storms, drought, rain, all of them are becoming more severe as a result of climate change. And climate change is also affecting certain regions of the world. Some regions are getting more water, and some regions are getting even less water. And in those regions, diseases are transmitted by insects more readily. Air quality is in general poorer around the world, and food security is lessened, especially for those people who really want food and live for example, in most of Africa, as well as water stress is even becoming worse than it is due to climate change. So here's the reason. One reason is that our planet is warming up. This is 1951 and this is 2022. Okay, almost 2 degrees difference in the average temperatures around the world, and in certain regions it even reaches almost 3 degrees. on average for that region. So that's one reason temperatures are rising. CO2 emissions are rising. Okay, if I was in a hospital and I'm a patient, I would be dead by now with any indicators that go up like that. So I think that this is something to consider for us. The water problem is in the industrialized countries, such as the United States, we don't feel it as much unless you live in some of the dry states. But around the world, you can see here the red, the dark red. I mean, this is a crisis, right? Almost a quarter of humanity is experiencing water crisis, not water stress, but water crisis. That means they don't have enough water to live or eat. And so in the year 2040, almost 5 billion people on our planet will be experiencing water stress for at least 3 months out of the year. Okay, and I should know what water stress is because I grew up in one of those red regions in Amman, Jordan, where there is very dark red. Okay, we're in trouble actually in Jordan because we don't have enough water. So the American Psychological Association has a term that describes the present state of affairs, and they call it eco-anxiety. And especially young people are bothered by this, and it's worrying them. And I tell you, when people that young are worried about the future, we're in trouble. So, but I'm an optimistic guy because I believe in the power of human innovation. And I also think that I don't think humanity has ever faced a problem where society says we've got a problem and we're determined to solve it, that it was not solved. I don't know of any problem like that. And so I think air, which is plentiful and cheap and free, holds the answer, okay? We can take CO2 out of the air and make clean air. We can take CO2 out of flue gas and make clean energy. And then, if possible, we can take water out of the air and make drinking water. So I suspect that in the near future, as we advance in these technologies, that we will be talking about what I call the air economy, is that there will be industrialization of air and the components of air and the manner with which we can take out CO2 out of the air and clean the air and water out of the air. So these are the two things, two vexing problems facing society that I want to talk about today. Carbon dioxide taken out of air to make clean air, or taken out of flue gas in power plants before it reaches the air, and water taken out of the air to make drinking water. I chose chemistry because you can make stuff. No other discipline can actually craft a material on the atomic molecular level except chemistry. And chemists have honed in the skills of taking atoms and molecules and crafting them so that we can make pharmaceuticals, okay, which change the quality of life for many people around the world. And plastics, for better or worse, plastics have made accessible a great deal of products to the largest number of people around the world. So those are just two examples of how great things could be if we can navigate this periodic table of the elements. What I want to show you and what we have invented at Berkeley is a way to take molecules and stitch them together into new materials. And not just one molecule, but many, millions of molecules to make an almost infinite number of materials. That's the subject of today's lecture and how these materials are solving the carbon capture problem and the water problem. Okay, so let me just think in terms of larger terms. I would say that the advance of civilization relies on how well we design materials. Okay, that's true when you think deeply. And for example, in the Stone Age, that was true. In the Iron Age, got better. And this is the wood. This is playing with wood. This is a big building in Sevilla, in the south of Spain. And of course, semiconductors are a perfect example of how precise change in or precise design of the material could really advance civilizations, plastics. And what I want to say today is that when you can do this on the atomic and molecular level, as we have been doing here at Berkeley, that's the ultimate control of matter. And these are the 21st century materials, because there's no other class of materials where you could do this. So this chemistry, we call reticular chemistry. We've developed it over the last 35 years. In the mid-1990s, we discovered the first members of materials that started out this chemistry. And the chemistry basically linking molecular building blocks by strong bonds to make crystalline structures. Let me explain. We want building blocks so that we can play Lego, molecular Lego. We can design things. We want strong bonds because I want that material to be in a power plant, not for days, but for years, so that I don't have to replenish it. And I want them to be crystalline so that they can behave homogeneously in their action. So that in this case, as you will see, there are porous materials, and so all the pores are homogeneously sized and they behave in exactly the same way. But also for chemists, when you have crystals, not only are they beautiful, but you also can characterize them with great definitiveness using X-ray and electron diffraction techniques. So the first class of materials we made in this way are, we call them metal organic frameworks, or now they're called MOFs. I named them back in the mid-1990s, and I was excited when people started calling them MOFs, and I realized that if you ever have an acronym and that you want that acronym to stick, not only do you need good science behind the acronym, but you should have a vowel in the acronym. Then it becomes a word. Okay, so we made MOFs, and MOFs are made from these blue units. These are metal oxide units that are linked by organics. That wire-looking thing is an organic unit to make an extended structure. Okay, I'm just showing a fragment of the structure, and the yellow ball is not an atom, it's just an illustration of the space within this structure where we can compact hydrogen, carbon dioxide, gases like water, all kinds of things. Or we also invented covalent organic frameworks. These are the all-organic frameworks. Okay, they're the dream for organic chemists, for chemists in general. And you guessed it, they're called COFs. And we also, and I won't talk about this today, but I just want to show you the sophistication with which this chemistry works. We also can make woven structures, molecular weaving on the molecular level, interlacing of organic threads in and out of each other to make organic fabric, solids that can carry out dynamics, okay, and have tremendous implications on improving the mechanical properties of materials. So I won't talk about that today, but I want to focus on MOFs and what they're doing in terms of, in context of those problems I discussed. The strong bond building block approach is the key and is at the foundation of this chemistry. So I'm showing one structure because it's a prototypical structure, but MOFs are many. Thousands of them have been made. This chemistry is now being practiced in over 100 countries around the world. Okay, and the result of that has been to be able to vary the length of the linker, the size of the linker, the functionality of the linker, everything that an organic chemist or a chemist can vary can be varied here. The same thing for the multimetallic unit, the same thing for the pores, the size of the pore, the geometry of the pore. And when we go in and install chemical entities onto that backbone, we can also design the chemistry of the pore so that I can craft the interior so that it's ideally suited to pluck CO2 out of the air or water out of the air, okay? So we have an infinite frontier. The possibilities are endless. There are almost 100,000 MOFs that have been made now in the community, and hundreds of applications ranging from energy, water, biotechnology, medicine, cancer therapeutics. They are all being investigated. And these are atomically precise, ultra-porous crystals, and we have shown over the years that they are architecturally, thermally, and chemically stable, meaning that I can actually put them in the desert to trap water out of the air for many years, or CO2 out of power plants for many years. If your eye could see on the molecular level, you would see something like this. This is a MOF. It's made from these gray units, that's the organic struts, and from the pink units, these are the metal oxide units that join those struts together. It's a scaffolding. And we know from our studies using X-ray diffraction that everything you're looking at here is an adsorptive site. And what I mean by that a gas molecule can come and sit at every spot that you see here. Okay, and that means that they have extremely high surface area. In 1 gram of this material, there is 6,400 meters squared per gram. That's the footage of 1 gram. That's about a gram of this material, okay? There is a space covering that the size of a football field, okay? And I chose the Cal football field to illustrate that. So if I take that gram of MOF and I spread it into its atomic arrangement, it will cover this entire football field, and actually more if you calculate, more than a football field. So what we have been able to do with this chemistry is that we make this material, this is what it would look like. Their granules are crystalline, they have well-defined shapes. And if you zoom in into one of these granules, one of these crystals, you'll see, and we can characterize this by X-ray, you can see the struts and the joints. And if I'm a molecule permeating through this crystal, I can see that it's completely open, and gases that fill very large volume could be compacted into the pores. Why would they be compacted into the pores? Because the pores are designed to have stronger interaction to those gases than the gases to themselves. So they like to be in the pore rather than bumping into each other outside the pore. And so it's almost like a room full of bees, and you introduce a honeycomb, that is the MOF, and bees land on that honeycomb, occupying much smaller volume. That's what I mean by compacting gases. So the materials, we've been working with a chemistry giant, BASF, to scale up the materials, and now they have a plant that produces MOFs in multi-ton quantities. And this is what one of the MOFs look like, the one that I have kept showing you the structure of. They look like baby powder, okay? But like I said, a gram of that material each granule is riddled with molecular pores that have the surface area of a football field. So they can be shaped into many different shapes depending on the kind of application. The state of art in this chemistry today is that you can imagine a structure. Anyone can imagine a structure, even those who are not chemists. And you can go to the laboratory and make it. Okay, the building blocks are available, you make it, you study it, and eventually build systems that can serve society. And that's what's going on in Berkeley, in my labs at Berkeley. We take molecules, we make materials out of them, we configure these materials, put them in a shape or form, engineer them into the ideal form that can be integrated into a system. What I mean by system, a product that actually does something directly impacting on a societal problem. So I call that the reticular chemistry innovation cycle. And so now I want to show you how that cycle works. With carbon capture. Carbon capture problem is divided into roughly two major problems. One, taking CO2 out of the air. Okay, there's a lot of CO2 in the air, but it's dilute, right? So it's a difficult problem. Even though it's double what it was since the Industrial Revolution, it's still dilute, so it's difficult to take it out. We need to take it out. Even if we stop burning fuels today, fossil fuels today, we still need to take out the CO2 out of the air because it's causing the warming and the damage, acidification of the ocean. So the second problem is to take CO2 out of flue gas, power plants that burn natural gas, produce 5% of their flue gas as CO2. Those that burn fossil fuels like petroleum and coal will have about 16% CO2. Okay, easier problem than air, but still they're both difficult. It's just air even more difficult. Okay, so could we do this? What do I need to do to even qualify to be in the running for solving this problem? I need a material that has high capacity. If it has high capacity, then it gobbles up CO2, lots of CO2, so that I don't have to do so many cycles for that amount of CO2 to be captured. Water stability, because water is everywhere. It's in the atmosphere, it's in flue gas, it's a product of combustion. Oxidation, the oxygen is around us, so the material has to be oxidatively stable. Cyclability, you need to be able to do more than one cycle. In fact, you need to do hundreds of thousands of cycles, okay? Regeneration temperature, you don't want to take the CO2 in and then it gets stuck, that you have to heat up the material to hundreds of degrees Celsius to remove the CO2. That's energy intensive process. That's not going to happen. And scalability. It can't be a boutique material. It has to be scalable to multi-ton, hundreds of thousands of tons. And the devices have to also scale because the problem is very large. So the bad news is there isn't anything out there that meets these requirements. Okay, there are a lot of people working on a lot of these, and there are pilot plants being built, but they're not viable in the long term. They are illustrating that you can do carbon capture, but they're not the way to commercialize. And MOFs are even, I have here MOFs maybe, but I'm biased. Okay, I'll tell you why there is another check mark here. But I think MOFs can solve part of the problem, but not the problem of carbon capture from air. So let's talk about this. I just want to show you how MOFs take up voluminous amounts of carbon dioxide. This is at room temperature and reasonable pressure. In one tank filled with MOF, I can store the amount of CO2 that would be in 18 tanks. Even though the MOF occupies volume inside that tank, but because the pores are programmed to compact CO2, put CO2 molecules next to each other by virtue of their interaction to the framework, I can store 18 times the amount. So capacity is no problem. But CO2 doesn't come in pure form. Okay, so I have to do something to selectively remove CO2 from a mixture. And to do that, I design a MOF like this. Okay, here's a MOF. Okay, it's made from metal oxides and organics as I described below. But if you look closely, you find that the pores are decorated with green dots. These green dots are amine units, NH2 units that are covalently bound to the backbone. The chemists call it primary amine, CH2, NH2. And these amine units, no matter how little CO2 you have in the air, they can seek out that CO2 and take it out. Okay, because they are base and CO2 reacts with NH2. Okay, but you see, because of the porosity, because MOF is a scaffolding, it is replete with these units so that you can store or you can capture a lot of CO2. Okay, we did a lot of studies. I'm not going to go through a lot of graphs, but I can show you a prototype that we built in our lab based on a kilogram of this MOF. Okay, the kilogram of the MOF is here. We call it the sorbent. And we expose it to air. We call it simulated air. It's exactly the same components as air. And you see here it has 0.4 millibar of CO2. You could call it 400 ppm CO2. That's what it is in air. And as the air passes through this kilogram of MOF, it goes down to 20 ppm. So I removed most of it. It became toxic air, became healthy air. Okay, the same thing with flue gas. 15% CO2 goes down to less than 2% CO2. This material works, right? It works. It works under real conditions. It takes CO2 where you have water along with the CO2 in mixture, you have nitrogen, you have oxygen, and it plucks out CO2 and only CO2 not being complicated by anything else. That's the power of crafting materials on the atomic molecular level. The real test of a viability of a material is to take a bucket of this MOF and expose it to a wave of air and see what comes out on the other end. Very simple experiment. It's called breakthrough experiment, okay? Meaning that the gases break through the material and then the CO2 is stored in your solid. And in this experiment, you can see that this material takes up over 1 millimole per gram. Over 1 millimole of CO2 per gram of material. Why is this important? It's important because computations by industry show that if you have a material that takes up 1 millimole per gram or higher and can cycle 100,000 cycles, you've got a commercializable material. So we're very close to solving the problem. Except life is not that simple. Because we cycled, in our prototype, we cycled 10 cycles and we were excited. It's cyclable. We cycled 20 cycles. It's great. 100 cycles, it's great. 200, very nice. But when we hit 500, the material started taking a nosedive, meaning it started decomposing. Why? This material is stable in water, stable in acid. In fact, we can make it as a superacid. But it turns out that because of all those amine units that we decorated the pore with, that's a base. And so the base was destroying our material. Okay, but I have faith in humanity and innovation of especially innovation of my students, because we anticipated this years ago and we invented COFs back in 2005. COF's backbone is carbon-carbon backbone. So nothing is going to destroy this material in the chemistry that I just described. So here are the amines that we attach to the backbone, and this is the result. The result is not as good as the MOF for air captures, 0.3 millimole of CO2 per gram of material, not one. But remember, in this one, we don't have water. When you have water in there, this number doubles. So take it from me, we are at 0.6 millimole per gram. And this material can be cycled. Okay, we are doing the cycling for this material. And in terms of flue gas and coal, the problem is solved. That's easy. That's much easier than. So we're making progress. Let's say we have the materials in place. We need to scale them up, but the tests on their stability, cyclability, and the level of uptake are within reach. And I can tell you that our lab has, with COFs, has reached higher than 1 millimole per gram, but I'm not ready to talk about that yet, okay? We just learned this in the last couple of weeks, so I'm very, very excited, and the scientific problem is solved, and if society is serious about capturing CO2, we have the materials here. MOFs, although not good for carbon capture from air, but they're brilliant for capturing CO2 from cement plants. Cement plants, 1/3 of the CO2 emitted from industry is emitted from cement plants. There, the percent CO2 in the flue gas is up to 35%. Well, a MOF, just a regular old MOF, works for that beautifully. And it's been cycled over 450,000 cycles with a capacity, depending on the conditions, 2 to 4 millimole of CO2 per gram. That problem is solved because this is now being scaled up to multi-ton quantities for a company in Canada called Svant that is already deploying this in cement plants. So I'm very excited that some of that CO2 will not reach the atmosphere. And the problem, this really difficult problem, it looks like solved. For cement, it's solved. And as I mentioned, for the other, for air, we're almost there. Okay. Now I want to turn to water. The red regions here, except of course the cold regions, are also water stressed because all the water is frozen. That's why it's red in this plot. But you see the rest of the world with red is water stressed, as I said before. If I can make a material that takes water out of the air in the red region, that where the humidity can go down to almost 10% relative humidity, maybe even lower sometimes in the desert. But where people live is around, the lowest is around 10% relative humidity, typically 20%, 30% relative humidity. Nothing works there in an economic and energy efficient way. So if I can design a MOF that takes up water under those arid conditions, it will work even in the blue regions where there's plenty of water, but the water may not be clean. In fact, it will work even better there. So our idea is, could we design a MOF that works anywhere, that takes up water from the air anywhere in the world at any time of the year, regardless of the weather and conditions? And before you ask me the question about drying the air, there's plenty of water in the air. There are almost 13,000 cubic kilometers of water in the air at any one time. Okay, so if I serve each one on this planet 50 liters of water a day, I would have only used a fraction of 1% of the water that's in the air, because there's plenty of water in the air, as much as we have in lakes and rivers on our planet. There's a lot of water in the air. Okay, what's the problem? The problem is illustrated in this psychrometric chart. You have a water vapor and air plotted on one side and temperature on the other side. And I've colored the water conditions in green and the other ones in pink, okay, or brown. Let's imagine that I am in Granada, south of Spain, very beautiful place, but very dry, okay? I have relative humidity 20%, and I am at 30 degrees Celsius. For me to take water out of that air, I need to cool the air down to 4 degrees Celsius. That's a lot of energy you have to put into the system to cool all that air down to 4 degrees C. Now let's imagine that I have a MOF that takes the water out of the air, like CO2 out of the air, but concentrates it in the pores. And now I take that MOF with lots of water in the pores and I put it in a box, seal that box. I've created humidity. I've created high humidity. Okay, so that's what the MOF does. The MOF concentrates water in its pores, and now you have higher humidity. And for me to take water out of the air in C, I only need to reduce by a few degrees Celsius to condense that water. So the MOF, in many ways, takes desert air and makes it tropical air, so that you can take the water out of the tropical air with energy efficiency. We discovered this when we were studying CO2 and water, the dichotomy between binding CO2 in the presence of water. So we were studying also the interaction of MOFs with water. And the student came in with this red plot. Okay, I was shocked because I noticed that it's taking up water at very low humidity, at around 20% relative humidity. And it was taking it in a cooperative mechanism. That's why you have this extremely sharp knee. It's not a shallow, but it's, as soon as one water gets in, everything rushes in and you saturate the pore. That's a cooperative mechanism. It's similar to oxygen interaction with hemoglobin in our body. The other amazing thing was that I can take that water out of the pore by heating to only 45 degrees C. Okay, that meant to me, being raised in the desert as a boy, I understood that maybe I can take this material, expose it to the air at night to take water out of the air, and during the day when it's hot, I can take the water out of the pores and make drinking water. That's exactly what we were thinking. And before we did that, we wanted to show that water can move in and out many times, and so we cycled 80 times. But we noticed something, that after the first cycle, there was a slight drop in the capacity. Then the capacity was maintained. And so we wanted to figure out what's going on there. And so chemists are very good at nitpicking into structures and characterizing structures. So we found that in fact the first water molecules are binding strongly to the hydrophilic sites that are attached to those metal oxide units that I was talking about. And these water molecules, illustrated in red here, they act as seeds to extract other water molecules from air and build up the water structure in the pore as you would with ice, except at room temperature. Okay? So what I'm trying to say here is that the first water molecules attach very strongly to the hydrophilic sites, and they sit there, and they act as seeds onto which other water molecules hydrogen bond, and you build up, filling the pores with water. When you take the water out, you're not taking the seeds out, but you're taking all the other water out. The seeds stay in the MOF, directing basically the traffic and building up the structure. That was a discovery. Without the material being crystalline, you wouldn't be able to look at that. So I wanted to illustrate that, in fact, this can work outside the lab. I don't know anything about engineering. Okay, in fact, in my youth as a graduate student, I was told not to think about engineering because that's not so intellectual. Okay? And so I said, okay, I need an engineer to help me build. Of course, they were wrong. They were very wrong. Engineering is amazing, as you'll see. So I took this problem to my colleague at MIT, Evelyn Wang. I had a joint program with her on something else. I said, let's build a handheld device to show that, in fact, this MOF can work outside the laboratory. And we discussed what is needed and everything. She built it, and we tested it, and it worked. Okay, we used 2 grams of MOF, and you can see the water coming out of the MOF, almost the MOF sweating, basically. We didn't collect a lot of water because it was only 2 grams but it worked. It worked outside the lab. So this was amazing. You can make water with no energy input aside from ambient sunlight. And so we published this in a very high impact journal, Science. There was a lot of publicity about it. And MIT gave a whole bunch of money to Evelyn and said, don't work with Omar, just we'll develop it here, okay? And so, but the material is everything. Okay, the material is a Berkeley material, and you need that material to make any device. And so my heroes, my students, became engineers, okay? They weren't stopped by an engineering problem, and they designed a very simple system, a box within a box. The small box has the MOF, the outside box, you can open it and close it depending on whether you're at night or during the day. So during the night, it's open, air goes through the MOF, MOF extracts the water out of the air. You close it during the day, the interior gets hot, water comes out and condenses on the walls of the material. You can harvest water, okay? This is what it looks like, plexiglass, 1 box of plexiglass inside another, very cheap, very inexpensive. And they rented an SUV and drove from San Francisco all the way to Arizona to test this device, okay? I had Doug Clark write a letter that this white powder, a kilogram of the white powder and all those wires, thermocouples and everything, that everything is okay, this is nothing to be suspicious about, in case they got stopped by the sheriff. Okay, but they were there, and I asked them to call me when they saw water condensation. And they didn't. And it was 2 o'clock in the morning, and I'm very worried that the experiment is not working, okay? So I called them at 2 o'clock in the morning, and they said, everything works fine, except when the water comes out, we can see the cloud, but it doesn't condense. They can see the water vapor coming out of the MOF, but it doesn't condense. And of course, having grown in the desert, I knew that if you dig 3 inches under the ground, it's a lot cooler than the surface. So I said, well, dig up, put it under the ground, and we will see. So they didn't do that. That's the wonderful thing about students, is that they never listen to the professor. So They went to Home Depot and they got soil and they covered it with soil. And indeed, they got condensation. You can see the condensation here. And they collected about a cup of water. Okay? No energy input aside from ambient sunlight. You're taking dry air or low humidity air and you're making a cup of water. And we tested the water for any metals, organics, anything. And it's purer than any water you will ever find, actually. You cannot find water more pure than this one. Even biotechnology water is not as pure as this one. Okay, so because the MOF itself is a filter for water, and the water goes through the phase change. And so this student drank it.
2, 3, action. Cheers.
Okay, thank you. Yeah, that's it. Thank you. I don't need this anymore. Eugene is Ukrainian Russian. He's still alive and doing just well. He's actually running a startup on commercializing this. That MOF is a zirconium MOF, and zirconium is the cost of a MOF is roughly the cost of the metal. And so zirconium is about $150, $160 a kilo. So and I have been telling you that MOF chemistry is very flexible. You can design anything you want. So we went for the aluminum. Aluminum is dirt cheap. And these nice organic molecule, very widely available. It's not an exotic molecule. We made another MOF that works just as well. In fact, it works, as you will see, a little bit better. And the MOF is a miracle MOF, because if I'm a water molecule floating through the pores, I'm experiencing hydrophilic pockets and hydrophobic pockets, hydrophilic and hydrophobic. And this hydrophilic, hydrophobic gives you the right balance between things sticking too tightly and things not sticking at all, and therefore allows you to take the water at lower temperature. So, make a long story short, we scaled it up. It turns out that in the first experiment in Arizona, air wasn't getting through all the MOF. It was a cake of MOF. Now we use thinner wafers of MOF, and we took the device to the Mojave Desert, and here the students became more ambitious and attached a solar panel to the device to allow for power for a fan to push air into the MOF and then heat up the MOF to get the water out. Okay, so that they can do more than one cycle a day. And so this is the result. This is the water that came from Berkeley, so ignore that. And this is the water that they harvest in the desert during the day and during the night. And you see the humidity can dip down to almost 10% relative humidity, less than 10% actually. And you're harvesting water during the day and during the night. And you have to make a video to show that in fact this thing works. So this is dripping water in real time through that almost a kilogram of MOF. They harvested 1 liter of water per kilogram of MOF per day. Okay, and that's not the full capacity of the MOF. It's just our engineering is not so clever yet. Okay, so we're learning. Now we can engineer something more professional. And now we have a device the size of a microwave that has a door. The door opens, water goes or air goes in, it touches the MOF. You can see the MOF also takes water out from the MOF, and then the device collects the evolved water. Okay, you can see puddles of water at the bottom, and now you're filling it up. Guess how much MOF this device has? 200 grams. And it's harvesting 5 liters of water a day. 200 grams of MOF producing 5 liters of water a day. Okay? And the MOF, we have done now almost 350,000 cycles with it in the California desert, and the MOF is completely unaffected by the uptake and release. And so it's functioning, and it's graded to last for 5, 6 years, maybe even more. Okay, that's the lifetime of the electronics of the device. And at the end of this journey of the MOF, you can disassemble it by adding strong acid and reassembling it into that material in water, okay, with zero discharge. So this is very, very exciting. So I've talked to you about two kind of devices. One, completely passive, okay, that sits in a corner and harvests water 1 cycle a day. And I talked to you about an electrified device, that's this one, where you need less MOF, but you do more cycles to make the water. So one more experiment, just to drive the message home, is that these 3 students went to Death Valley to demonstrate that this new MOF we made, the aluminum MOF, works under the harshest of conditions. And they designed a system where you have pancakes of MOF that are stacked along this direction. They're spaced from each other to allow air to move in and out and water to move in and out. And so it works. You should be able to see bubbles coming up, water coming up. You see that? Okay, it means that the MOF works under the humidity here is around 10% relative humidity at 127, I think, degrees Fahrenheit that day. Okay, so if I use MOF 303 as a standard, I can look up the weather conditions around the world and tell you how much will be delivered each month of water using MOF 303. And so you see here liters of water per kilogram of MOF per day. And the Atacama Desert, which is the driest desert in the world, in August, the driest time of the year, you can deliver 7 liters of water per kilogram of MOF per day. But you can plot it also for other Lanzhou, Kabul, Riyadh. In Riyadh, a typical dry place, about 40 liters of water per kilogram of MOF per day. New York, Stockholm, Los Angeles, London, Granada. Okay? It works. And this is how the water goes into this MOF. This is one of the pores. I'm going to slice it in half, and you're going to see the water goes into the hydrophilic pockets first. Fill those, and then bridge over the hydrophobic. And that's the push-pull of water that allows you to take the water out under at lower temperature, okay, in an energy-efficient way. So these are the pores are filled, okay, and this material already is being scaled up to multi-ton quantities by BASF. So I'm a chemist, and I'm thinking, all right, I made this structure. If I could increase the uptake by 10%, then 10% more people in the village could have a drink, or in the town could have a drink, right? So could I expand the pores to have more water stored? It turns out that if you expand the pores too much, the behavior of water changes and becomes not a so efficient material. So how do I keep the properties of this material, the adsorptive sites, the characteristics of this material, the same, but still add more water by stretching the linker? And it turns out, through AI, which really didn't give us good guesses, but it triggered something in our mind, that you can do what I call a long arm extension. You add 2 carbon atoms to this linker. This is MOF 303. The linker is here. If you add 2 carbon atoms there, you get a material exactly the same as MOF 303, but just slightly bigger. And it takes up 50% more water. Okay? So now if I have a ton of MOF 303, I will deliver 500 liters of water for each cycle. If I have a ton of this LA MOF, the long arm extension MOF, I can deliver 750 liters a day from 1 ton. And that's the reality of what I am talking about. These are the plots that show that in fact has the same structure. It takes up more than 50%. And the water, because of the 2 carbons are slightly hydrophobic, the water can be removed at much lower temperature than MOF 303, and it's cyclable. So now we are becoming more and more aggressive in scaling up this. And this is a conception of a device. I like passive devices that don't require power, don't require electricity, because the capacity of the MOF is huge. So this one has a battery only to allow you to open the door and close it. So that you're laughing. We need engineers, okay? We're learning, okay? There are materials that probably do this without power, but anyway, so that's our plan. Is that I showed you the smaller devices, but now we want to scale them up and to capture that capacity that I've been describing. At the end of the day, we're really giving people water independence in the world. You can have your own water by having a device at your home, either in your kitchen for drinking or outside for household needs. It does not require power. It might require a battery to open a door and close it. But I want to repeat, 1 ton of this material is as large as your refrigerator in your kitchen. Okay, 1 ton of material will give you 750 liters of water for each cycle. If I have the battery that opens the doors and closes it, I can do 3 cycles. So 750 times 3 liters for that ton. So this is very, very reasonable expectation. The fact that the MOF stays in the device for years means that the price of the MOF is negligible. It's an aluminum MOF, for God's sake. Aluminum is like $2 a kilo. So this cycle works, and we developed the chemistry at Berkeley that makes this cycle complete. But we're not done, because we want to speed up this cycle. Okay? It took me 35 years to get here. Okay, I don't want the next generation to take 35 years to make the next material. So we want to speed discovery and scale it, make it available to everyone in the world. And that means we need robotics, we need AI. So we need this cycle, we need the digital cycle. Okay, we need these 2 cycles to work together to speed up the business of discovering material, the business of engineering them, the business of building those systems and making sure they're energy efficient, the mass transport is appropriate, the air management, all of those things that engineers do, we can automate it, we can compute from the molecule all the way to the system, to the performance of the system. And so I teamed up with one of the greatest people I have ever met, Jennifer Shays. If you have not met her, you need to meet her. She's one of the most inspiring people, and she's a Berkeley professor. She's the dean of the newly inaugurated College of Computing, Data Science, and Society. We teamed up with her, and within 1 week, we raised lots of money to build this Baker Institute of Digital Materials for the Planet, and it does exactly, the mission of that is to couple the digital cycle with the innovation cycle. And so the scientific mission is to integrate AI, data science, machine learning with the experimental sciences to speed up development of sustainable systems and scale their impact. Make research widely available and speed it up. Because today we have carbon capture problem, water problem. Tomorrow, the next generation will have other problems. So we need to build the basis for making chemistry work faster. This is my last slide before the acknowledgement slide. ChatGPT, okay? It's a nice little tool. We use it not in science, but in our daily thing for amusement, okay? But we can, in my lab, using ChatGPT and using simple conversational language, make ChatGPT assistant. This assistant can actually mine information out of MOF papers. It can mine the way people are making MOFs and the conditions under which they make MOFs. Okay, so we can train it to recognize chemical formulas, because chemists, when they refer to chemicals, some of them refer to chemical formulas, right? Chemical formulas, some of them have common names, some of them have proper names, some of them have abbreviations, and so on. So we can train ChatGPT to recognize these variations. And what a student can do in a year, ChatGPT can do in less than 2 weeks with 95% accuracy. That's better than my accuracy if I had to tabulate that information. Why is this powerful? It's powerful because I, as a researcher, now I have this information before me. The facts, I have all the facts in front of me that I can interrogate, machine learn, whatever. So now my decisions are not based on chemical intuition. They are really based on facts. And all decisions made based on facts are better decisions than the ones that are made by chemical intuition, because chemical intuition, if you talk to students and you ask them to justify their answers based on scientific basis, when they talk about scientific intuition, you find that the scientific intuition is not based on science. Okay, it's based on feeling. So this is going to remove that from our thinking so that we, the students, the researchers, can make decisions about how to discover things, how to pursue observations based on facts. That's why it's taking my students, or chemists, I don't want to pick on my students, they're great. It takes them 2 years, 3 years to crystallize a MOF. Why? It's no need to be trying all those different conditions now you can do it in 2 weeks. ChatGPT supervisor, if they get stuck in making a MOF, they're not getting the observations or the product that they want, ChatGPT can suggest several options of what might be wrong and actually give you instructions, which solvents to use, which things to do, what to filter out, what other starting materials you could do, what modulator, all these things that I would advise my students, ChatGPT can do. And then ChatGPT Research Group, everything that you need to make a new MOF, ChatGPT can do, okay? It can identify the starting materials. It will tell you how to make it, how to make a MOF. It will consult machine learning algorithms, modify the machine learning algorithm, give you instructions to how to make 3D printed vessels to do your reaction, analyze your data, and in the end, in this paper, which hasn't come out, we show that in fact, in the end, it leads you to making a completely new MOF. Okay, so this is a revolution, I think, and we're either on the train or not on the train. And it's gonna speed up chemistry, it's gonna speed up particular chemistry, and to get to materials that can solve society's problems. So now you see why I am optimistic. And so when society identifies that we have a problem, we need to solve it, and we have the will to solve this problem, science and chemistry in particular can create those materials that can address those problems. So these are my heroes, my students. I want to thank them for all their hard work and for putting up with me and the financial support. And thank you for your attention, and go Bears. Thank you for coming. I'm happy to take a few questions if there are some. Okay, I think she has a microphone there.
Hi, thanks for the talk. It was quite fascinating. You mentioned carbon capture and water vapor, but not hydrogen.
We work on hydrogen. Yeah, we are working on hydrogen. We can store. Okay, let's use the tank analogy. In a MOF, in a tank filled with MOF, you can store double the amount of hydrogen at 77 Kelvin. Okay, it's not 20 Kelvin, but it's a heat wave compared to 20 Kelvin, where hydrogen is liquid. But this is very interesting for mobile application. At room temperature, we can only, and that's 12% by weight. That analogy means that I'm storing hydrogen at 12% by weight. At room temperature, that material does around 2.5% by weight. We need to get to 6 weight% to make it viable for automobile fueling. But definitely hydrogen, of course, hydrogen is the ultimate fuel, and especially Japanese automobile companies are very interested in hydrogen storage. So we have an active program on hydrogen. All I can say is that we're not lacking in ideas, but sometimes those MOFs that we want to make are hard to make. So that's why I am bringing in the AI in a big way, because I think that that will facilitate making those MOFs.
Can you speed up electrolysis or make it more efficient with the MOF? By heating the water and just capturing some free hydrogen or something to that effect?
Yeah, I mean that not with MOFs, but that's already a commercialized process actually. Yeah, for the production, not the storage, but production.
There's a question back there.
With the advance of AI, should they still be focusing on like learning wet lab skills and physical doing chemical skills, or is it all computer?
I think I would say we are experimentalists. So we need to experiment with new tools that emerge. AI is a tool. Right now, it's a tool that could speed up what we're doing. In the fullness of time, when there is AI for science and it's very robust, it might even give us insights and good guesses or good predictions as to where we should go. So I encourage the coupling of these two, the coupling of the experimental techniques with AI. But in reality, why use the archaic method if you can get AI to help you with that? Robotics, I mean, and AI to help you with that. So I am of the, I like to throw things away. You know, in my house, if you come to my house, it's almost like those sample houses when you go looking for houses in new development. There's absolutely nothing around. I throw everything that is not needed away, and I keep everything clean, because I think when new things come out, we need to be able to adapt them, and science should operate at the same pace that society operates. Otherwise, we risk being ignored by society, and that would be dangerous for the practice of science. So science right now, we are moving at geologic chemistry. For the most part, we're moving geologic scale compared to society and compared to other disciplines. Okay, so in the chemistry department, we have a big push towards AI so that we can do the things that need to be sped up using AI. That doesn't mean it's going to take over our thinking. Nobody, in my thinking, cannot take over our ability to be very heterogeneous and very different, okay? And the fact that we make mistakes is actually, in itself, could be very creative, could be precursor to creativity. So I'm not worried there, but I am worried that our students come in to do MOF chemistry to my lab, and I tell them to slow down to geologic scales and learn archaic methods, when in fact they could take advantage of ChatGPT AI tools to speed up and improve what they're doing and make more observations and acquire more facts. Yeah.
Hi, you've got me thinking that captured CO2, carbon rather, is in little Legos, and then what happens then? Where do they go then, when you've captured the carbon?
Very, very good question. Well, right now, we don't have a robust commercializable way of taking CO2 and converting it into something useful, like fuels or whatever, pharmaceuticals, starting materials that society needs. So right now, you basically pump it under the ground. Oil companies use it to pump more oil out of the ground, okay, which is crazy. But there are colleagues of mine already working on methods of taking CO2 and converting it through, let's say, microbial genetic engineering of microbes, taking CO2 and turning it into enzymes, proteins, pharmaceuticals, fuels. That's one direction. Another direction is making catalysts that could take CO2 efficiently into feedstock materials that could be used as starting materials for many things like pharmaceuticals. The science in both of those is not yet deployable on a very large scale, but there are pilot plants already being built based on these two techniques. So our attention is focused on not just capturing the CO2, but also converting it. And if you can do it within the MOF itself, then that's fantastic. Yeah.
So, what are the energy requirements for carbon capture?
Well, the energy requirements right now for the material that has been used for the last 70 years to separate CO2 from a natural gas, which is using amines, is like in a power plant, it would be almost 1/3 of the power plant output because you're heating up water. Heat capacity of water is 10 times the heat capacity of a MOF. So in a way, the MOF, because it's a solid, you're saving a lot of that energy, okay? So I would say that's why there is a big push around the country, including by the Department of Energy, to deploy MOFs. Yeah.
I'm sorry, that's all we have time for, but thank you so much, and thank you to everyone for coming today.
Thanks, everybody.